Good afternoon, or good evening to those of you in Europe, and apologies to those of you in Australia. Welcome to Session 3 of the ESIG 2020 Fall Technical Workshop, being held online on Tuesdays and Thursdays during the month of October and into early November. I'm Charlie Smith, the Executive Director of ESIG, and I will provide a few brief opening remarks. As with so many things we were planning to do in person this year, our plans were derailed by the coronavirus, and here we are online again. The workshop was planned with the input of our ESIG Offerings Committee, chaired by Bethany Frew of NREL and Julian Matevosyan of ERCOT, who is also our session chair today. The committee consists of the chairs of our 6 working groups and several of our board members. We have a great set of volunteers who make ESIG what it is, and we encourage you to become involved if you're not already. Regarding logistics, I would ask you to note that the webinar will be an hour long. We will have 3 individual presentations of approximately 12 minutes each, and we plan to hold the questions for a 15-minute Q&A session after the last speaker, except there's been a small change of plans because our first speaker has to leave shortly after he finishes, so we'll take questions for Fred at the end of his time, so please keep that in mind. As we are doing with all of our webinars now, we'll be using the Slido platform for managing the Q&A. We would ask you to use Slido for your questions, as you will not be able to ask your questions through WebEx. You should go to slido.com on your device and enter ESIG6 as the event code to ask your questions. Please be sure to indicate the person to whom you are addressing the question. The instructions are also in the background slide for the webinar, and you'll be reminded by the session chair. You'll see a thumbs up button next to the question on Slido to allow you to vote on prioritizing the questions submitted. So please keep the questions coming during the presentations, and we will address them at the end, except, as I said, for Fred. Recognizing the limitations of a webinar with typically more than 100 people on the lines will be muted. So again, we ask you to use the Slido platform to ask your questions with ESIG6 as the event code. Session 3 today deals with a very timely topic these days on challenges with weak grids and low inertia systems. We'll hear several different angles on this topic from several of our European colleagues and from ERCOT. The session will be chaired by Julian Matevosyan of ERCOT and co-chaired by Megan Miller, who works with Julia. Julia, as I mentioned, is co-chair of our Offerings Committee. She is also chair of our High Share of Inverter-Based Generation Task Force of the Reliability Working Group and a regular contributor to ESIG activities. Megan is a planning engineer at ERCOT in the Dynamic Studies Group. Her current focus is on distributed generation, which includes revising ERCOT rules and deciding how to incorporate DG in planning. Julia is a longtime friend, and I look forward to Megan becoming one too. Julia and Megan, we appreciate having you here today, and I'll now turn it over to you, Julia. Julia, I think you're still on mute. I'm not hearing you.
Yes.
Oh, okay.
Can you hear me now?
We can hear you. Yep, now we got you.
Sorry about that. Good afternoon, everyone. Good evening for those in Europe, and thanks so much for joining. Charlie, thank you for your kind introductions as always. So as it was discussed in the opening session last week, there are power systems around the world that reaching very high levels of inverter-based resource penetration, which are well in excess of 50%, and there are parts of interconnected systems where in a part of the system you'll have more than 100% provided by inverter-based resources, such as, for example, in South Australia. With that, I think the topic of today's session requires no introduction. However, as Paul Danholm alluded to in the last week's session, it's not really about inertia or system strengths in particular. It's about getting to very high levels of inverter-based resource penetration while still maintaining stability and reliability of the grid, and figuring out the point where we can no longer rely on synchronous generation for maintaining voltage and frequency stability, and it's time for inverter-based resources to fit that role. So today we have a great lineup of presenters covering the challenges that system operators such as ERCOT are grappling with already today. moving on to emerging solutions that are underway in national grid electricity system operator, and then on to looking at a little bit future-looking work with conclusions and recommendations from EU-funded project MIGRATE that investigated what it takes to bring a power system from where we are today all the way to 100% penetration. So without any further delay, I would like to introduce the first speaker, Fred Huang. Fred is the manager of regional planning at ERCOT. He's been with ERCOT for the past 14 years, primarily working on dynamic studies and assessment of stability impacts from high penetration of inverter-based resources. Fred, the floor is yours.
Thanks, Julian. So hello, everyone. So it's always good to have another opportunity to provide a brief update about our work in ERCOT related to the renewable integrations. So today, I think with a very short time, I would like to quickly provide a few updates and also a few items we are working on and to share with you. So the first one is always kind of very quick, high-level update. I think most of the gentlemen, ladies on the probably are familiar with ERCOT in general, but kind of a quick high-level update is from the renewable perspective. We kind of start calling it like inverter-based resources. In the ERCOT region, it's still mainly the wind and the solar today. So from the table, you can see as of 2020, by end of this year, we believe the connected and the one committed plan to connect to the ERCOT transmission grid is going to exceed close to 31 gigawatt from the wind perspective, and at the same time, we also start to see the increase of the solar integration into the ERCOT transmission grid. So by 2020, it's about 6 gigawatt. So as you can see, total by 2020, we are going to have close to 40 gigawatt the inverter-based capacity. Given ERCOT system, the peak load is around 78 gigawatt, and the of peak load, it can be as low as 35 to 30 gigawatt as well. So moving forward, look at the queue of the future projects, their interest and their commitment status. I think within 2 years, by end of 2022, we still see quite a good growth or in both the wind, particularly solar as well, within 2 to 3 years. So I think by close to 2022, I think our capacity of inverters likely is going to exceed 50 gigawatt from system-wide connected to the transmission grid. And as you can see from the location-wide, most of the renewable resources, they are located in West Texas. Currently, based on kind of average-wide, 75% of renewables of wind farm and 90% of solar, they are all located in West Texas, which kind of far away from the load center in ERCOT system. So that is something we need to kind of address and have a very quick introduction later. From the record perspective, I think the highest for renewables typically is like during the midnight. So the maximum output, we were close to 21 gigawatt. And from the penetration perspective, compared to the load served at the moment, the record got recorded. It's really close to 60% penetration, but 60% of the load were served by the wind generation at the moment in real-time operations. Another typical one, I think, for your region, if you also have a renewable start to connect to or has a lot of experience, I think the trend may be applicable to any other region is the implementation for the renewables just comes so quickly. So based on our typical observation, the record shows from a renewable from the beginning to the commercial operation, it can happen within really 24 months. And for some pretty well planned and aggressive projects, it can be even possible to finish within 18 months or even shorter. So that's really provide another kind of quite a bit system change and involve the more dynamics overall from the planning perspective as well. So in addition to the renewable, but I think from the weak grid perspective, I think in our system, most of the renewables, they are located in West Texas. So really the combination of the far away from the load center, and we have limited and potentially no synchronous machine could say online, especially during the high renewable output condition. And all the like, resources in that area, they are all inverter-based, essentially power electronics. So kind of you put the three combinations together in West Texas, I think weak grid is kind of definitely the one we need to be aware of. So essentially the challenge for the transfer of the renewable from West Texas to the load center, typically the two primary concerns we need to handle is the voltage stability, obvious, and the second one is a weak grid. So when we have more than close to 30 gigawatt or more concentrated in West Texas without or with a very limited synchronous machine, the voltage is going to be very sensitive, and the signal may not be robust enough for the inverters to reliably synchronize with the grid. So over the last few years, I think and these are the typical options we has been conducted and identified, even implemented into West Texas, just to improve the operation of the renewables under kind of weaker grid related concerns or conditions. So the first one is we do with the PSK studies we conducted a few years ago. We identified a weaker grid, just the controllers could not operate functionally. They needed more robust health signal. So as a result, we implemented two synchronous condensers, particularly located in a panhandle region, to provide one, system strength, and the second, the dynamic relative support to improve voltage stability and the system strength at the same time. On top of the condensers, voltage stability, especially the dynamic one, is also important under weaker grid condition. So SVCs and additional system strength improvement, like the transmission, new circuits, that's also kind of was under the condition, and now they are implemented as well. So this slide is going to give a very quick overview. When we start to have addressed the weaker grid system, from the assessment perspective, in addition to typical steady state and positive sequence dynamic analysis, we do see the need to perform the more detailed EMTP analysis. So in fact, we conducted a PSK study. The first one we started back in 2016. Focus was to evaluate the panhandle region where that area we only have a transmission circuit and renewable generations. There's no nearby synchronous machine. They don't even have a nearby load to be served. So it kind of in 2016 stage, that area kind of really a renewable zone to provide a lot of renewable generation to a load center in ERCOT. So by itself, the weaker grid is the one we need to assess and identify if there's any issues. So also identify the positive sequence tool at the moment we have may not be adequate to perform the analysis like this one. That's how we started a PSK study. So really the PSK study, we start to conduct it regularly up to today. And really we use a PSK study to help us on three major categories. The one is similar to other tools to help us identify, assess system stability. And also use a PSK study result to help us identify the improvements that may not be easily identified through other assessment tools, such as steady state or positive sequence analysis. So as an outcome, as I mentioned earlier, through the PSK studies, we identify and recommend the synchronous condensers to be incorporated into the panhandle region to improve the system. Also, at the same time, with the PSK study, help us to recognize the value and the benefit for the inverters to have closed-loop voltage control. So in ERCOT, all the renewables connected to ERCOT transmission grid, they are required to provide a voltage support, and also they are required to control voltage at the point of interconnections. So if they are capable to do this one and well coordinated with the neighbor wind farms and the solar farm together, from PSK study under weak grid condition, we do see the benefit to improve the system dynamic performance. And like in many other regions, before you consider the weak grid condition, you would like to have some tool or indicator to help identify whether the system is weak or not. So in ERCOT, we have a weighted short circuit ratio application and the index to help us to evaluate the system stress in the panhandle region. So to make sure that the index and the associated application can continue to be used, we also perform the PSK studies, just really compare the detailed EMTP result versus the identified threshold of the index to make sure the application can still fit or is any adjustment is necessary based on the system condition. So this is kind of very high-level overview. This is kind of an example of the most recent PSK study we conduct for the panhandle region, focus on the weak grid condition. So this is kind of a very typical setup because the size of the study case is relatively big. So it incorporated all the transmission buses, is more than 100 buses, and incorporated close to 10 gigawatt inverter base. Everything they were detailed model inside the PSK. So as you can imagine, the setup, the computation burden, the whole study kind of process is not kind of cannot be done like in days. So it typically take a while to finish the study and analyze the result. So as a kind of example, we have, based on the recent PSK studies, one of the, I would say, the concern we have is with the system with more inverters and the need with the PSK study may require large scale, the complexity and the computation and the FT burden start to definitely kind of increase almost like exponentially. So we start having like a need to think about what are the potential options we can continue improving. So as of now, I think the PSK study is still necessary for us. But moving forward, in addition to this one, I think the challenges of large scale certainly is something I would say, probably the whole industry, they are looking for kind of improvement as well. So kind of the key takeaway to share with the kind of the group is, although we start to focus on a lot of efforts on the PSK, the EMTP, more detailed analysis, but I think it is also important to kind of make sure the typical tool we have, they are still critical and they still provide a lot of value to identify the system performance and the issues and even identify the potential solutions. So steady state and the typical dynamic stabilities, they should still continue to be considered, at least in our applications. So those are the ones provide a lot of values before we just directly jump into the PSK studies. And as I mentioned earlier, we do see the potential need to start to increase the study scale of the PSK to be potential system-wide PSK studies. Definitely the challenge is is very time-consuming and consider the potential need for close to real-time support. So it may not be practical to fit that the operation needs as well. And the last one is the more study is needed, and obviously the model is more important and critical. So this is kind of for your reference. We continue to improve the models, work with our stakeholders. And the example on the slide here, just a very recent proposal. We try to have a more like a system-wide and a systematic approach to have a PSC/PSK model validation and verification improvements. And this proposal is currently under ERCOT market rule revision request review. So once this one is approved, we do expect we'll get a benefit and a great improvement on the models in both PSC and the PSK. So this is my quick update. I'll be happy to take one or two questions. Thank you.
All right, thanks, Fred. So I guess the first question that is asked on the slide is, what is the current percentage of IBR-based wind generation in ERCOT? Are doubly fed induction generators considered 100% IBR?
We do consider, actually, from the IBR perspective, so far our inclusion is type 3, type 4. So type 3, they are also included in the IBR capacity.
Okay. And moving on to the next question, how much additional reactive power support was provided by the synchronous condensers in the Panhandle?
I think the condenser size is around 175 MVA. So the reactive is around plus 125.
Okay. And this next one is, how would the availability of grid-forming inverters affect the situation in the Panhandle?
Well, that's a very good question. I think we are also looking into this one. I think the next two presentation will provide more details and good information. I think from our perspective is, the first one is we need to have a model to get a better understanding right in the case. The challenge we have is we don't have a lot of information available to us. So I think we try to kind of learn from other regions as well. But so far, we don't have other information over the model for us to evaluate the potential benefit of the new technology or new control algorithm.
Okay, great. Thanks. If we have time at the end, Julia and I might try to answer some more questions for Fred, but we'll move on. Thank you, Fred.
Thank you.
All right. Thank you, Fred. We'll move on to the next presenter, and it's Julian Leslie. He's head of networks at National Grid Electricity System Operator, in charge of planning of Great Britain electricity transmission network to ensure that it remains future-proof for decarbonization, and also that currently connecting generators are able to stably connect to the network when needed. Julian, take it away.
Great. Thanks, Julia. Hello, everybody. I'm speaking here from Great Britain, so it's currently 7:30 in the evening. So just going to spend the next 10 minutes just talking around some of our investigations into virtual synchronous machines and grid-forming inverters and some of the learnings that we've found from that, and what is our approach to ensure that the market is delivering us a safe and secure and reliable system. I'm sure from this audience this afternoon or this evening that this slide is pretty familiar with you all. I guess the key thing is on the very right-hand box there, it's ensuring that the virtual synchronous machine just allows the converter to really act like a voltage source, which really makes it look like a synchronous machine. And it's absolutely critical that it needs to react in very, very quick timescales, and therefore making sure that the VSM can supply those fault currents, but also, more importantly, contribute to system inertia. I think when we looked originally at virtual synchronous machines back here in GB, what we recognized was that if it didn't have a source of energy that can sort of support the inverter and the power electronics, that actually it didn't meet the needs for us here in Britain. I know that'll be different wherever you are in the world. But we certainly needed a position where the VSM plus the related technology, which includes the energy source, can really help to improve inertia on the system, short circuit in feed, the voltage stability, but also helping to support the volts and the fault ride through during the fault. Obviously, they're not quite the same as synchronous machines. We don't quite have the laws of physics kicking in to manage in a fault situation and immediately post-fault. But actually what we have proved is that these virtual synchronous machines do act and behave very much like a synchronous machine, which is helping us to sort of transition from a predominantly coal and gas powered system into a very much a renewable system. So yeah, some of our characteristics of the network in the UK is that we're a 50 gigawatt peak system. Even at this time of year when it's getting darker and a bit colder, we're still only sort of 35, 40 gigawatts. But we've now got 17 gigawatts of wind on the transmission system, 10 gigawatts of solar embedded on the distribution system, and probably 6 or 7 gigawatts of wind on the distribution system also. So there are times, and there's certainly times over this summer, with a reduction in demand due to COVID, where we were regularly seeing 80% plus of zero carbon generation. And that does include our nuclear fleet that we have here in the UK also. So we've been at this challenge for quite some time. We started really thinking about the future and how the non-synchronous generation was going to impact on the system. So in 2013, we started sort of considering this, understanding what was out there, understanding whether we would ever be able to move away from synchronous machines and find some power electronics sort of alternative to that. We've collaborated with many sort of universities across Britain to sort of come up with key research and investigations. And then finally, really in 2018, we established this expert group. And it really got us to a position where we could define a specification for a grid forming sort of synchronous machine. And it's not just a virtual synchronous machine, as I said earlier. The key thing here is that it's a virtual synchronous machine with some form of energy store, and that was key to us. So that was in 2018. In the UK, we're very much market-led with everything that we do. So what we did in 2019, so just a year ago, we did some analysis to see how we could define the need on the system for these long-term stability products, which includes inertia and short-circuit in-feed. And that led us then to, at the back end of 2019, so just about a year ago, we ran a tender where we put out a requirement for stability, grid inertia, and fault circuit in-feed to the market. And we let the market come forward with its ideas for how it could meet that particular technical need. And that was hugely successful. It was phase one, so it had to be delivered within a year and a half of the tender, so by April of next year. And this first phase has really delivered us a lot of repurposed plant. So we have got gas turbines, which are just spinning their turbine, but without burning any gas, for example. But what we're really excited about was last week, we launched phase two of the Stability Pathfinder work, which is for delivery in the next 3 years to give it the market participants longer to design something. And we really believe that virtual synchronous machine and grid forming will be parts of that solution. But again, we are technology agnostic, so we don't care what the solution is, as long as it can meet the technical requirements. But we do have, in Scotland, we have one full-scale wind farm that is developing and testing the proof of concept. And that has been live on the system now for probably close on to a year. So we're getting lots of great data working with the wind farm operator and the university to really understand how that VSM machine is working. So through all of this research, we've now, if you Google the GCO 137, which is a change to our grid code, so our technical code of how we operate the system and the requirements of connecting. There's a link there which you can follow, and that we've been able to get to a position where we can define that minimum specification required. So that means anybody now who wants to connect to the grid system in Britain can see what it is that's needed and therefore they're able to design and to develop their own technology, whether that be a wind farm, a HVDC interconnector, a solar farm, or whatever else it might be that can provide these grid services to the grid. And as I said earlier, we're very much a believer in markets, and therefore there'll be a commercial reward for that type of response. So this specification really talks about the ability to have, of the plant to have grid forming capability, so i.e. the ability to operate as a synchronous rotating voltage source, and the ability to supply inertia power, phase-driven power, damping power, and controlled power output. But it does, and I must stress this, it does need an energy source. So the VSM without an energy source doesn't provide us really with the inertia, but obviously it is valuable for fault-in feed and the provision of synchronizing torque. But from our perspective, it doesn't provide us the full grid forming response that we need in order to operate a secure system. So I've mentioned already the EOI, expression of interest for phase 2 in Scotland. So this is a market position which is now open, and we set out the real technical needs over the next 4 years, running out to the next 10 years in Scotland, so the very north of the country, which is very, very high penetration of renewables, with the idea that by this time next year, or even sort of by the early summer of next year, we will have contracted possibly up to sort of £500 million worth of contracts for the market to go and to deliver 10 to 15 products and devices across the network that allow the short circuit in-feed and stability required for the operation of the grid in Scotland. So that was a very short and brief introduction to grid forming and virtual synchronous machines and the activities we're doing here in Britain. So with that, I'll hand back to Julia.
All right, thanks so much, Julian. We'll go to the next presentation, and then hopefully we'll have time for a lot of questions that are coming through Slido. Keep posting those, and please don't forget to put the name of the presenter that you have this question to. So the next presenter is Thibault Prevost. He is a system stability expert at RTE with French TSO. He has been working on renewable connection studies and grid code requirements, and is now working on stability of systems with high penetration of renewable resources through European project MIGRATE and OSMOSE. Thibault, the floor is yours.
Thank you, Julia, for the introduction. So I'm glad to present just after Julian, so I'll be able to skip some of the slides. So I'm going to talk about the MIGRATE project, especially work package 3, which was about the operation of a system with high penetration of power electronics and even 100% power electronics. So basically, the work package 3 in the MIGRATE project was about starting in a system with 100% penetration of power electronics and going backwards a little bit regarding the penetration and see if we can put some synchronous machine in the system. So it's kind of a reverse approach that has been taken in other work packages, and also, for example, a different approach that was taken in National Grid ESO, but we'll see that we come to the same conclusion. So what we wanted to do, in fact, by having this 100% power electronics, was kind of reset our brain from having synchronous machine on the grid, because as a system operator, we have been used for decades to have a synchronous machine, and in fact, most of our operational rules are based on the fact that we have synchronous machine. So what we have ended up is, what is a grid forming? What do we need? And as Julian said, we need to have a stiff voltage source behavior, which means that you should not vary as soon as you connect a load. So you need to be robust against phase jump. You also need to be robust against frequency change. So you need to provide some kind of inertia. You need to be strong, because you need to be like a reference signal for other sources that like to synchronize on you, like other grid following units. It can be other synchronous machines. It can also be other grid forming. And in the MIGRATE project, we consider that we don't need any telecommunication or synchronization. You also need to provide current during a fault, but as the grid forming is provided by inverters that have a very limited overcurrent capability. You need to have a smart current limiting strategy to avoid jeopardizing the system stability as soon as you reach your maximum current. And of course, you need to be able to handle some islanding, at least for a few seconds, to leave some time for other mechanisms to come into the game. So what we have done in MIGRATE was to ask 3 universities to develop kind of grid forming control. So they each developed it independently. So they ended up with 3 kinds of controls. Some of them are well known, like the filter frequency group, which is very well known, for example, in microgrid. The virtual oscillator, that is quite the strangest one. It takes the self-synchronization properties of pendulum and apply it to inverters. And the matching control just match the equation of a synchronous machine with the one of an inverter with a DC bus and a capacitance. So they ended up with these 3 different controls developed on very simple test cases. They have been eventually made open source, so if you want to play with it on MATLAB, you can download them. We've worked on theoretical stability of transmission systems, so basically inductive network, and under very basic grid assumption, like having a load flow that is not too high and enough connectivity, you can have a proof of stability on that. So we have multiple other controls in the literature that are grid forming, like the virtual synchronous machines that Julian mentioned. But in this project, we did not focus on one control. We did just focus on these 3, and we tried, in fact, to develop them independently and then see how they work together. So the first result on a very basic simulation, like small fault, here are the results of the different controls. So you see that even if the controls look kind of different when you look at how they were designed, you look at the behavior of all the electrical values, eventually they really look the same. So when we got this result, what we did is connect them on a small system that kind of looked like a transmission system. Why? Because you have a meshed topology, you have double lines, you can have small and big inverters, like a very big load connected to small inverters. And in fact, we took the 3 controls and plugged them on this network without tweaking them before this connection to see how it would behave. Luckily, they all synchronize at the first shot. So for us, it was a very good hint that in the future, a different manufacturer developing different controls based on very simple requirements, like the one that Julian just mentioned, but formulated in a slightly different way, that would be able to operate all together. We see that here we have a line opening, so the angle need to rearrange. We have the frequencies that deviate in different directions, but they very quickly resynchronize. Here we have a fault, even though the current here is going a bit too high because the final current limiting strategy was not implemented, but still they resynchronize quite fast after the fault. So one of the key findings that we have here is that, in fact, the inverters, they are like Ferraris. They can go like really, really fast. But if you want to have a stable and robust system, especially as in the MIGRATE case, we don't use telecommunication. In fact, we use the power lines as communication between inverters to synchronize. So we should not try to go as fast as we could. And in fact, it can be translated exactly as the frequency and the voltage magnitude should not change too fast in the inverters. And it's exactly what Julian mentioned in his previous presentation. You need to be robust against phase shift and frequency shift. We were, in fact, surprised to see that in a small signal, all this grid forming control behave in a very similar way. So it might even be possible to harmonize the controls, at least in small signals. Regarding the fault current, in fact, one of the main subjects of this MIGRATE 4.3 was how to protect inverters during event. Because when you behave as a voltage source, as soon as you do a small transient on the grid, like on this very simple case, you just strip one line without doing any fault. You have on the left a big inverter, on the right a small one, but a big load connected close to the small inverter. By just stripping a line, you have an overshoot of current that goes above the nominal. So it's very important to have a smart limitation of that. If you just go for a current limitation, you might end up with oscillations that would jeopardize the system. So we have a hybrid control that in fact first saturates the current for a few milliseconds, and then you go to a virtual impedance control, which in fact decreases the voltage reference, but then you go back to voltage source behavior. And it allows to have a stable system and also to reduce the current. So this control has been tested many times in simulation and then implemented on a reduced scale hardware. So here is the mockups that we had. If you're interested in the result, all the deliverables are public. You can go through them. So we had this, it's with a 7 kVA inverter when we can plug all the controls that were developed in MATLAB, and we have a transformer, and then we can plug it directly to the distribution grid or to an amplifier. More tests. So here is a result of a voltage fault for 400 milliseconds, and we see that the current is just hitting the 1.2 per unit. That was the limit of the inverter that was set also in the controls. So even with some measurement noise and like real installation, we managed to have a very nice current limiting that fitted the 3 controls that were developed, which means that it could probably be plugged to any kind of grid forming controller. Now we have talked about this 100%. How about the transition to 100%? We've seen that, in fact, having grid forming inverters on a system with synchronous machine would release the stress put on the synchronous machine. So for a synchronous machine, it's better to have grid forming inverter rather than synchronous machine as a neighbors. Why? It's because the grid forming inverter acts faster, and so they take their burden much faster than if there would be a synchronous machine. Another interesting part is that if you want to have a specific purpose, like limiting nadir or limiting the rock-off, it would be more efficient to install a grid forming rather than grid following or grid supporting inverters. Grid forming being faster, in fact, you would need to install less MVA. Other interesting part is that being digital controlled, inverter can be updated remotely, and also you can adapt the anterior services and the gains and the inertia you would provide depending on the generation mix, even if it changed within days. One interesting part also is when you reach very high penetration of inverters, you might need to retune some of the machine controls. Why? Especially the PSS control. PSS were designed for a system where you only have synchronous machine and where you have, I would say, slower oscillation. If you go to a system where you have only inverters or almost only inverters, the oscillation that you would have as a system would change, and therefore it's quite obvious that you need to retune this system stabilizer. As a conclusion of Work Package 3, we see that operating a system with only inverter is possible if you have at least a few grid forming inverters on the system. So we see that the grid forming function, in fact, can be kind of unifying because they behave exactly the same way in small signal. You can describe with very basic requirements something that would fit the purpose and would make the system stable. So we have at least one current limiting strategy that can protect any sensitive power electronic device working in grid forming. So we think it's very good because it would avoid overcost that could be linked to oversizing or transient overcurrent. So we know that grid forming inverters are technologically feasible, at least from a small scale, and as Julian said, we have demonstration also for a wind farm, tens of megawatts that operated for a few months in grid forming. And we also carried out a cost analysis and compared grid forming inverters to a synchronous condenser on a French scenario. It was for 2035, and we ended up with costs that were roughly the same. So the choice between grid forming inverter and synchronous condenser is at least not based on So as I said, the transition to very high penetration might need specific attention for the remaining synchronous machine and a few updates of the parameters. So this were the conclusion that we had last year because the MIGRATE project ended in 2019. And now I will just say a few words on the OSMOSE project, which is kind of a follow-up project of MIGRATE, at least one of these work packages. In work package 3, we have a demonstration of grid forming inverters. And one of them is a 1 MVA inverter that will be connected to our grid. So it will have all the controls that we developed within MIGRATE. So we have this filter droop control. We have the current limiting strategy. We changed a little bit the current limiting strategy because in MIGRATE it was only developed for 3-phase fault, and here we have to deal with the unbalanced fault and also unbalanced voltage. So we kind of also dealt with the unbalanced and harmonic stuff. And on the DC part, we have a hybrid system with a battery and spare capacitor. So why did we do that? Is because we considered that the battery would behave as roughly as a grid following unit, and the supercapacitor would behave as a grid forming. So it will be the supercapacitor that will do this inertia stuff. It will deal with all the fast transient and will not age the battery, and the battery can also be considered as an old model that would have been upgraded with a supercapacitor. And so this inverter has been tested in the factory in July. It has been installed early September in our substation. So we see here the pictures of it being installed. Sorry, one is flipped. And we are presently doing the site acceptance test. So here we see that the different control parameter of inverters for the battery and the ultra caps to see how fast the response of the two will be. But here we'll have this demonstrator of grid forming inverter connected close to a big customer that has so big motors that will start every morning and switch off every evening. So we have a huge transient. We also have close to it a hydropower plant that is started a few times a year. So we'll manage to have a very interesting data out of that to see how efficient it is and how robust it is when being connected on the grid 24 hours and 7 days. Thank you for your attention. And Julia, what is yours?
Thanks so much, Thibault. Very interesting presentation. Megan, can we switch to questions now? There are a lot of questions coming in.
Yes, there are. Yeah, so if anybody else has any others or want to upvote any, go to Slido. Okay, so the first one I'm going to ask is at the top of the list for Julian. So are you locked into VSM controls on grid forming inverters, or are you open to more advanced controls? And there's very similar, are you losing capabilities by using the VSM concept? GFMs can do much more than just mimic synchronous machines. So is VSM limiting?
Yeah, I mean, a couple of great questions. I mean, we're still investigating. What we try to do in setting the specification, technical specifications, is to be broad enough that we get the minimum, but not so constrained that actually we stifle innovation. So obviously we don't design these things. We just need to make sure that as the market comes forward with solutions, that we can find a way to work with them and that they work and support the system. So we're open to any sort of technology, any sort of uniqueness that comes forward with any sort of new innovation or different types of controls and fast controllers and whatever. So I think the key thing is that we set out our requirements on the system, and however we meet those requirements, then we're technological agnostic to that. And we have been very cautious with our specification that we're not locking out any innovation. There's more to come, really, and we're really market-led on that.
Great. Okay, so for Thibault, how will system protection operate with limited fault current?
There was a specific work package MIGRATE about protection where I was not involved in, but basically there was upgrade of distance, allows them to behave in a better way than how they would today. But basically, they also say that having having differential protection would solve the problem, because differential protection don't really need high current to work properly. If you're more interested in that, you can go to World Package 4 results that are available on the MIGRATE website. I'm sorry for this short answer.
All right, thanks. Okay, so back to Julian. You mentioned inverters inertia can be adjusted. Is this feature being used in actual operations in National Grid, and how is it adjusted?
Sure. So with our test sort of wind farm up in Scotland, we're certainly adjusting all of the sort of controls and operations just to see how it impacts on the performance of the wind farm. So I'm not sure of the detail, because obviously some of this is confidential information for the developer of the wind farm as well. So we are looking at how we can adjust it and the impact that has in real-time operation. Quite how they're doing that, I'm not sure. Members of my team possibly are, so if necessary I can follow up with that, but I don't know at this point.
Okay, thank you. So back to Thibault. How soon will grid forming inverters be needed on the European grid? At what % grid forming will we start to see benefits?
Good question. Will we need grid forming on the system? I would say maybe if you give me when will the typical power plants, like conventional power plants, shut down, maybe we could know that, but for now we don't exactly know when. We saw that, for example, in 2035 in the French scenario that we have, where we have the highest share of renewable, at some point of the year, where we will need either grid forming unit or synchronous condenser, but we would have a system that would be at risk. And when do we start seeing the impact of grid forming? I would say as soon as you connect one, you will see the impact. If you're located close to the plant, you will directly see it.
Okay, thanks. So back to, we'll answer a couple of the ERCOT questions that came in. So there were several asking about PSCAD models. Fred's not available right now, but just very quickly, to answer a couple of these, the interconnecting customers are required to provide those PSCAD models. All of the models are user-defined and not generic models. And we have some revisions to ERCOT rules proposed that improve the model validation and verification process right now. Okay, so a couple of those we can take off of there. Going down, let's go back to Julian. On your slide 2, does that imply that grid forming device which uses a PLL in its control loop will not be classified as a grid forming device?
Yeah, so that was a key part of our initial research, because originally back in 2013, we didn't think that the DSM and grid forming as it was defined at that point, sort of 7 years ago, would be suitable for the GB system. But it certainly is, the technology has progressed and we've moved away from having a PLL that actually we feel as though for the GB system that moving away from PLL does mean it can be a grid forming device, and therefore with the PLL in the control loop, it will not be classified as grid forming here in Britain.
Great, okay. And so back to Thibault, what are DVOC and matching modes? How do they affect the system performance, or are they intended to perform better than droop mode?
It's quite hard to say that they behave better. As I stated in the presentation, basically in small signals they behave the same way. There is a specific part in the matching controls that directly links the frequency of the system to the DC voltage. So it could be an advantage because it means that you kind of know the DC voltage and therefore maybe the state of your storage by knowing the system frequency, which is a value that is shared throughout the system. I can't say which one is better or worse. In fact, they all have quite similar properties and very slight difference. Why we have this three control is just that we ask the same question to three different universities that use different approaches to try to solve it. And for us, it was important to see that in the end, we have a system that is stable and that all these different controls can work together.
Great, thanks. Okay, so our next question comes from Jose Canto. So to Julian, were battery systems considered as part of your VSM IBR program? Technical specs, models?
Yes, the batteries certainly are part of that solution. And what we're finding is that a lot of the existing wind farms, that they can upgrade the control system and stick in a battery, and actually they start to act like a VSM. So we're really excited about that because we've got gigawatts of onshore wind where if we can find a way to sort of enhance their performance, then we can stop having to purchase new capital investment to provide these services and sort of just reinvest in their kit that's already out there. In terms of technical specs and the models, I would have no idea. Again, that's owned by the developer. We're just looking at the technical performance. We don't know exactly what batteries they put in there or the size and scale and performance of those.
Okay, thanks. So for Thibault, is it mandatory to have energy storage when operating with grid-forming inverters?
Okay. In fact, in the MIGRATE project, we did not specify any requirements. But in the end, it is mandatory, except if you have a primary source that is connected on the DC side that inertially have storage, like a wind farm with the rotating part. You could use the inertia of the rotating machine. If you don't, you need to add some storage because, as we said, you need to behave as a stiff voltage source behavior. Therefore, when you have a phase jump on the grid, during a few couple of 100 milliseconds, you will need to provide more power that you would be supposed to. Therefore, you need to have at least a few seconds of storage to be able to provide this kind of inertia, which is not really inertia, but behavior that is very similar. So in the end, you need to have some storage. It can be electrical or mechanical or whatever, but you need some storage.
Okay, thanks. Okay, let's do one more question for Julian. So are you finding there are increasing problems with harmonics as the amount of power electronics increases? Any issues with that?
So, I mean, it's a great question. Obviously, I think that the power source is a bit more sort of spiky with a few more harmonics. And certainly we've experienced a reasonable amount of flicker up in the very north of Scotland where there is very little synchronous machines. So we are seeing an increasing problem. And we're having to increase our modeling capability in order to really understand these. But also what we're finding is the generic models that you get to represent the inverters that the supply chain may provide us, actually they're just not the right level of detail. So we're having to work much harder to get really into the nuts and bolts of the inner workings of the inverters and to really understand how they perform under all system conditions to really get this sort of dynamic assessment of how they perform really understood and then put mitigation factors in place.
Okay, and so one last item, it's a question for Thibault. Can you please share the open source code repository?
I will send it to you, and you can share it with the slides that will be sent to the organizers, to the participants. It's fine.
Okay,
yeah,
great.
I think that would work, yes.
I will do so.
All right. I think it's about time we wrap up. So I would like to thank all panelists for their great presentations, and we really had a great discussion today. I'm glad we had enough time to ask almost all questions, I believe. And would like to thank all of you for participation and for posting questions. I think it has been great updates on weak grids and low inertia systems and grid forming inverters and integration of high penetration of inverter-based resources. And I hope it has provided some stimulating thoughts for everyone. I would like to remind you that there are 9 more technical sessions that will be held during the remainder of this month and into early November. You can find the full schedule of the upcoming sessions on the ESIG website, and you are all invited to attend. And the next session is on hydrogen production and flexibility requirements, which will be held this Thursday, 5 p.m. Eastern Time. So with that, I would like to close this session, and thank you so much for your participation. Bye.